about a refresher for neural net fundamentals and backprop fundamentals. Okay, so here's our neural net. We have a input size of 3, represented here by x. We have a hidden layer of size 2, and then final output scalar value. X is mapped down into the hidden layer space by way of this W1 matrix, which are learnable parameters of the neural network. Similarly, over here, we map a two-dimensional space into one via this W2 set of weights. These neurons here obviously are split in two to represent the fact that after this initial, running the input through the weight matrix, we apply a nonlinear function to the output because we want our neural net, function estimator to be able to model nonlinear functions. And just basic matrix multiplication is just a linear transformation. So it makes if we did not apply a nonlinearity, we would not be able to model nonlinearities. And you can actually show, I think, that if we didn't have the nonlinearities here, that I think you can show that there's no need to even have hidden layers in here. If you're just doing like matrix multiplication stacked with matrix multiplications, I think that somehow reduces down into just a single matrix multiplication, although I'm not going to show that here. Okay, so that's kind of the architecture. This final activation is going to be our prediction, our estimate. And of course, what we're trying to model here is we're trying to model the probability of y given x, right? That's what this network is learning, a conditional probability distribution of y given x. Okay, so for our example, we have some toy data here. We'll take an example input x equal to just 1, 2, 3. We'll assume we already have either randomly or maybe we've initialized our weights like this, or we've trained them to this state. So we have W1 and W2. We have our label here, so this is a supervised problem. We have labels, in this case labels 1, and then we'll set this very basic loss function, which is just kind of like a squared error. Okay, so let's kind of walk through the forward pass of the network here. So again, we start with x, and we want to, by way of W1, compute Z1. So we can just start writing things out here. So Z1 equals W1 times x. Okay, and this is a matrix multiplication. So this is going to be like, the weight matrix 1 times the column vector x, right? Which we have here. We also know that this is a common type of matrix operation in deep learning, where you have a weight matrix left multiplied onto a column vector. And the way that I like to think about that operation is as a linear combination of the columns of W1 weighted by the values of x. And so I'll just draw that out once to illustrate. So one of the many ways you can compute this is like this. So we'll say equal to 1. Sorry, I'm not used to this tablet. 0.1, 0.4 plus 2 times the second column of W1 is 0.2 times 0.5 plus 3 times the third column, which is 0.3, 0.6. Okay, if you run this out, you will get 1.4, 3.2. Okay, now to move from z1, which we have these two values, over to a1. We're going to apply our nonlinearity, and we're just going to use a ReLU in this case. So a1, not a ReLU, a sigmoid, sorry, apply to z1. So we apply the sigmoid function element-wise to z1. So of course we get the same shape vector back, 0.802, 0.961. Okay, that's our A1. Now we'll apply the next step, which is the W2 matrix. So to compute Z2, Z2 equals W2 times A1, which is going to be equal to, in this case, our weight matrix has this shape, 0.7, 0.8, multiplied by 0.802, 0.961. Okay, and we can recognize this as a dot product between two vectors. 0.7 times 0.802 plus 0.8 times 0.961, and that's going to be equal to 1.329. Okay, the final step, we're going to use the sigmoid, maybe more appropriately here, to squash these so-called logits down into the range of 0, 1 to represent a probability. So we'll apply sigmoid to Z2, which will be 0.791. So this is our predicted, this is like basically saying like equal to our probability of y given x. This is our prediction. It's above 0.5, it's about 0.8. So we're like basically saying that like the probability of y being equal to 1 given this x, our current model is estimating about 80% probability, which is good because y is 1 in this case. So this is actually not a bad prediction. It's not, there'll still be a loss because this wasn't a 1.0, but overall not bad. So anyways, we can compute our loss now given the loss function we're working with, which again is not super realistic, but it gets the point across. And this is going to be equal to 0.0437 decimal place there. Okay. And again, obviously property of anything squared will always be positive, even though the value in here is negative. Okay, so this is the forward pass. Why does that? Let's talk the backward pass, backprop, how the model is actually trained and how it learns. Obviously the important part of this. So I'm going to focus on computing the updates to the W2 matrix. Just for the sake of the video, I'm not going to go and actually run the calcs all the way back to W1, but the same logic, the same flow that we'll describe can be applied. So this is what we call back propagation, which across the board in practice and research relies on the chain rule. So what is the chain rule to start? We don't really get into the derivation or anything. We'll take it at face value. The chain rule states it's like a mathematical property that we can leverage. So let's say you have some value y that is equal to this here. So basically, you have an input x, which is then first passed through a function g, and the output of g is then passed through the function f to obtain y. Okay, so that's our DAG if you will, if we want to compute the derivative of y with respect to x, so how does y change as x changes? We can, by the chain rule, it's the derivative of the outside function with respect to its input multiplied by the derivative of the inside function multiplied by its input. Okay, it's a multiplication. So like this is kind of like a mathematical identity property that we assume, and a nice way to write it, not like this. We would write it like this, right? So dy dx equal to df over dg multiplied by dg divided by dx. And, you know, visually you can kind of like simplify across these off, and here you go. Oh, why I always, one second. So this mistake that is supposed to be a y, of course. So dy dg multiplied by dg dx. dg's cancel, it leaves you with dy over dx. Okay. So that's kind of like a nice way that we can think about it. And again, this is the kind of core essence of Backprop. So what we're really interested in here, right, is we want to update our weights, our model parameters in W2 to increase the probability of the correct answer for this label. And, you know, I think importantly here, you know, the loss function is, you know, so taking this difference between the model probability and the label, you know, squaring it basically just to keep it positive. But the main point is that the loss function is the difference. So if we're outputting a high y hat for our one labels, you know, this difference will be small. If we have like a one label, but our model is predicting like somewhere near 0, that's going to be the maximum value. And same logic applies for if y equals 0. It's like if the model is predicting close to the label, this loss will be low. So like good leads to low loss, bad is going to be a high loss. Okay. And of course, we're never going to get it exactly on the money. So there'll always be some kind of loss, but again, we don't want to penalize things too much. And I guess like the way you could consider this is you want to envision, I guess you could envision this here. So like what does the, so okay, let's view, okay, so this, let's say this is like W1, 1, and this is W2, 2, representing the two dimensions of this weight matrix. So like this set of parameters, you could say live in like 2D space, okay? And so that we're viewing this plane here, okay? And you can imagine some kind of like axis coming out of the page here, which will represent as like some kind of topology. Oh, didn't know that was gonna happen. Okay. So basically, you know, this is going down into the page is lower and lower, and so like the kind of the, I don't know if I want to draw this in 3D, but the vertical axis, like z equals the loss. Okay. So, right now, our W11 is, oh, actually that should be, yeah, let me fix this. Sorry, this is supposed to be W1, 2, okay. So W, of course I would draw this wrong. Let me redo it. So this is like W21, this is W22, representing these two dimensions of our W2 matrix, okay? Right now we're at like W21 is 0.7, so we can say like maybe there somewhere. Here. And W22 is like a little bit further up, so you'll see like here, okay? So where do we live on this plane? We live somewhere around here. That's our current, where we live in the parameter space, right? Now when we compute the derivative of the loss with respect to W2, okay, what that gives us in this geometric representation is, well, I think it actually gives you, okay, it basically gives you this line right here, okay? So this derivative, as we'll see, will be a vector of the same size as W2. And so in that vector, we can visualize it in this same space, the same parameter space, as the kind of the direction of the maximum slope of this topology, which again is the loss function. We're assuming in this case that like the loss function is minimized at 0, 0, which of course that's probably not going to be the case. But when we take this, we actually compute this derivative, it gives us the gradient, they call it, in this space, and the direction of this vector, this gradient vector, will point towards, well, I guess technically it's not necessarily pointing at the global minimum, but you can imagine that there's some kind of slope of the surface of L, the loss function, here at this point, and it's pointing at the direction of like maximum ascent or descent if you just take the negative. Okay, and that's a pretty good indication of where we might want to move where we live in this parameter space. So like in this case, we are going to, hang on one second. So yeah, basically we are going to want to kind of take a step in this direction. Maybe move here, okay? And then, maybe next time we move here. And then eventually, we're getting closer and closer to we're decreasing the loss, right? by updating our model weights, basically. And again, it's possible, just basic calculus or geometry. If you have a function like this, right, where maybe this is the loss, and then you just have like a single weight in your model. If you were here, for example, right, you would compute the gradient and you would get some kind of indication of this slope here, right? And you would take a step this way, actually. So you might take a step here, and then here, and here. And eventually, you've found this local optimal local minimum. But of course, there is a better setting for W down here. But that's the nature of gradient descent, high dimensional nonlinear spaces, is that this is definitely a possibility. And so there's all sorts of ways that we try to prevent this from happening. There's basic gradient descent with some static learning rate that decides like how big of a step we take each time. That's what the learning rate is. And so we can, another example, right, is what you could do, what you wouldn't want to do, is you could, well, let's say that like, this function just like goes on and on and on, right? If your learning rate is too big and you start here, you could like, well, actually, let's say that like over here somewhere, like that's something like this. Okay, super ugly, but whatever. If your learning rate is too big, you could end up like jumping way over here into this territory where like every value is always going to be much higher than even this local non-global minimum, because you're basically bouncing around. Maybe bounce back over here, here. It's like unstable, right? Like you're not actually hill climbing this terrain. You're wildly jumping around. So that's a case of having too high of a learning rate. So, and there's things like the like RMS prop, the atom. These are all optimizers that do just basically like heuristic things you can kind of intuitively think of as like a heavy ball, rolling on this surface with some momentum versus like, this is called SGD, stochastic gradient descent, and this just follows the direction of the gradient exactly. Whereas like an atom or RMS prop will kind of takes into account like your trajectory up to this point. It kind of makes it so you don't always like just turn directly towards a gradient. You make more gradual turns in your path. So that is a long and drawn out discussion about optimizing neural networks via gradient descent, yada yada yada. But the point is, and getting back to the core of this video, is we want to know this value. What's the derivative of the loss function, this topology, with respect to our weights in the W2 matrix? because we're going to use that information to update our weights, to make them a little better. That's how we train the model. Just continue pushing data through it, through this process of forward pass, backward pass, updating parameters slowly but surely. And that is training a model. At some point, hopefully, you end up finding some low minimum of loss somewhere, and you stop training. And again, because across the data set, you're seeing a low loss value here. That means that you're pretty good at predicting the data. Now, of course, that could very easily dovetail into a discussion on overfitting, because technically, if you have a small enough data set and or a large enough, complex enough model with enough parameters, you can trivially just memorize your training data set, which of course is not what we want to do. But we are going to leave overfitting and ways to deal with that as maybe another video. So anyways, we want this value. That's what we're getting at, right? Okay, but we don't in Backprop via the chain rule. We don't compute this value directly. We can compute it via the chain rule, right? So we'll say like the derivative of the loss divided by, or with respect to, its input, which again was this y hat. Okay, multiplied by the derivative of y hat with respect to its input, which was z2, multiplied by the derivative of z2 with respect to its input, which was w2. Okay, now we basically can cancel here, cancel here, cancel here, cancel here, and there we go. We have d lost, d w2 matrix, okay? But we're not actually going to be canceling this stuff out. We're going to compute each of these separately, okay? So let's focus on derivative of the loss function with respect to y hat, okay? Okay. So what we want here, actually let me move this here. Okay, so derivative of the loss with respect to y hat. Okay, that's like, we can write this dy hat, and what is the actual, what is L defined as? Well, it's y hat minus y squared. Okay, so we want to know what the derivative of this is with respect to y hat. Okay, now you might recognize this as another application of the chain rule, because y hat passes through some functions to get here, right? Like first it's being passed through this like subtract y from it function, and then the output of that is passed through the squaring function. Okay, so what we can do is we can kind of like set a temporary variable, call it u, set to y hat minus y. Okay, and so then this is I can just write it out. G y hat of u squared. Okay. Well, we can even say like, let's say v is equal to u squared. So you write out derivative of v with respect to y hat is equal to the derivative v with respect to u times derivative of u with respect to y hat. Okay, this cancels out. All right, so what is the derivative of v with respect to u? That's just 2u, okay? Okay, the derivative of u with respect to y is just 1 per, this is like the variable that we're trying to take the derivative of, and then it's just subtracted by a constant in this case, so the derivative is defined as 1. Okay, so cancel the 1 out, so that's just going to equal 2 times u, which we set to y hat, minus y. Okay, so this is the derivative of L with respect to y hat. I'm actually going to get rid of L. This is the derivative of L with respect to y hat. Okay. All right. Anyways, so dy hat over z2. All right. Let's compute this term now. And what's y hat set to? Sigmoid. Okay. Now we can just go ahead and look up what the derivative of sigmoid x with respect to x is, and it's just in general x times 1 minus x. Okay, so that means that this here is going to be equal to, in this case the input here is z2, so it's just z2 times 1 minus z2. Okay, and dz2 with respect to w2 is the derivative with respect to w2 of the function w2 a1. Okay, which, we know w2 a1 is this kind of matrix form here, and without deriving it, we'll just take it as a given that in a situation where you have your variable of interest, you're trying to find the derivative of some function with respect to it, and it's sort of dot product with a constant here, a1. You can show that the derivative of this is going to be a1 transpose. Okay. So now, kind of computed these equations, right? And I think, in like Torch, AutoGrad, and things like that, these parameterized equations for the gradients of these components of the chain rule are pre-computed, kind of known by, I guess, probably just like if you consider the neural network as like a DAG, or a graph or something, you just need to know uh, the two nodes that are connected, what their operations are, and yeah, I guess they probably just have a whole catalog of equations for the derivatives of these things. So these equations are known in memory and kept around. So let's go ahead and compute these. So we can just compute this, right? So over here, right, d L d y hat equals 2 times y hat, which we had as 0.791. Oops. Minus 1. Okay. Negative 0.418. Okay. Here, we can compute this. So d y hat divided by d z2 is equal to z2, which we know to be 1.329 times 1 minus 1.329, which equals I'll have this written down somewhere. D y hat this is a 0.329. Had some inconsistencies here, so let me recompute this. Maybe something wrong. Something got switched up somewhere. But based on what we have here, this is equal to negative 0.437. Okay, and then this is going to be equal to A1 transpose A1 is this. So it's going to be like a row vector, 0.82, 0.961. Okay. All right, bring it all together. Now D, L, D, W2 is equal to DL, dy hat. 0.418 times dy hat dz2. Dy hat dz2 is going to be negative 0.437 times dz2 with respect to w2, which is going to be this. Okay, which of course equals some constant 418 times negative 0.47. It's going to be equal to some constant 0.182 times which is going to be 0.182 times 0.802. 0.146, and then 0.2 times 175. Okay, so this is the gradient. Okay. That's what we're after. And notice it's a vector in the same space as the W2 matrix. And so like in this space, like over here, yeah, I mean, actually in this case, looks like it actually is like, you know, if we're here, which is pretty accurate, you know, at 0.7, 0.8, you know, this is, looks like a vector that actually does point kind of like this, maybe. Okay, so in that case, like this visualization is pretty close. And you know, I think it's gonna be like W2 equals W2 minus some learning rate times gradient. Okay, so we're gonna subtract some scaled vector from this. Take this, this is a vector too, you know, technically this is a vector. And we're gonna subtract this vector, but flipped around, which means that we're gonna move kind of down the loss curve. And yeah, this learning rate is a hot topic in deep learning, like what do you set it to? A lot of times they'll change it with some sort of a schedule over time so that, you know, whenever you randomly initialize your weights and you have no idea where you are on this loss landscape, you have a high learning rate, kind of jump to like more different continents, try to find the lowest continent, like jump around a lot and then slowly decrease the learning rate and take smaller and smaller steps as you kind of hone in on your final destination. So, yeah, that is